Swayam Prabha. Digital India. Educated India.
Hi, so welcome back. So we are into 3D turbulent boundary layer formulation, right? And what we kind of stopped last time was looking at, we developed some integral relationships, and with the hope that we're going to get sort of a little closer to the solution, right? And again, we kind of are at kind of crossroads where we see that even a 3D well formulated integral theory is hardly easy, and we still have to solve PDEs. So we're kind of taking this up from there. Okay, so let us see that where we go from here. Okay, so some of the so what we're talking about now is the integral theories, right? And so what is the, so essentially if we are talking about integral theories, right? So this is needed, right? This is needed. So what is needed basically for integral theories are needed empirical correlations, right? Correlations to close the integral relations, to close the integral relations. Okay, and okay, let me write down a few, and then we'll look at a couple of figures. Okay, so so essentially this is something we should look at. Okay, so if you see here, okay, so unidirectional bidirectional skewing in 3-dimensional pressure driven boundary layers. So A is this one, unidirectional skewing and bidirectional skewing, and unidirectional hodograph, bidirectional hodograph. So you have this. So essentially this is something to kind of give you an idea, to give you an idea. So we have, see, the x-axis is right here, okay, the y-axis and the z-axis. Okay, so for a moment, just just overlook this part. Okay, just look at the x and y. Just look at the x and y axis. Why don't I do this? Okay, let's just say this is the plane that I'm looking at. This is the plane that I'm looking at, right? If I look at just that plane, then what you see in there, right? What you see in there is this, right? The velocity profile. This is the velocity profile that you're looking at, right? So when you go, this is your x-axis and this is your y-axis, right? And then, so this now, so this is the velocity profile, which this is a 3D case. This is the velocity profile in the x and y directions, right? So we are back. Okay, so essentially, so if you just look at the x, y, so this is very, in the sense that you will be familiar with what we've done earlier. Now in the so that is the u velocity. So and also this is the you can see the u velocity. That's what we were looking at. Okay, and then if you are looking just at the z and y axis, right, and again you see this velocity profile of w, but you see that this is not exactly, this shape is different from this. So that's why it's what you're saying is something called skewing. Okay. So this is the velocity profile in the component for the component W, right. W, which is essentially in the z direction, right. So this is unidirectional, skewing is skewing here, and if you look here on the other hand here, so this we have skewing in both directions, right. It's skewing both in the positive and negative directions. Okay, so this is the pressure driven velocity, the pressure driven boundary layer. Okay, now let's go back. Okay, let us see. Now, so the possibilities and what kind of complications we're looking at is that's what we are of concern, and the point is that okay, I understand physically that if when I draw it graphically or I physically I understand that. The point is now I'm trying to put some numerical theory behind it, where if when I calculate a velocity profile in this say z direction or x direction, right, I should be able to get what we just saw, right. Numerically, how do we accomplish that? What sort of equations do we solve? So that is what we are trying to understand here. Okay, so empirical correlation to closed integral relations. So now, for example, the power law profile. Right. The point is, how do we what is basically the how does the components of velocity within the boundary layer, which is small u and small w, right, how do they behave? So that's the profile. So power law profile, when I say which profile, so that's the profile we're talking about. Okay, something. So we use this, right. So this small u is the velocity within the boundary layer, right, which we just saw. So this is the u, right, this is within the boundary layer, and capital U is basically the component of the free stream, which is in the x direction. So similarly, small w is the velocity in the boundary layer in the z direction, and the w is the free stream component in the z direction. Okay. So this y by delta to the power n, right, where n is equal to h minus 1 by 2, h is equal to delta 1 star and theta 1 1. Okay. So well, we can one can remind ourselves as to what this is, right. So delta 1 star is displacement thickness in the x direction, right, and this is the momentum displacement thickness also in the x direction. So and we wrote down integral equations for this. Okay, this now this sort of a profile. Okay, this sort of a profile is okay. So the inference here is that this sort of a profile is this is reasonably valid, right, for modest pressure gradients. Right. So reasonably valid for modest pressure gradients. Okay. So these are pressure driven boundary layers, right. So this the pressure is basically, and this pressure gradient is basically modest. Okay. So poor approximation near separation point. Now, so we are going to get some simple simplest of formulas, right, which is what is plotted in the two figures that I just showed. So this will be the simplest of formulae. Okay. Okay. Now, number 1 is triangular, right, which is where we are basically saying the W component is equal to U by this tan of beta, right, for U less than U vertex, and 1 minus U by U, okay, tan phi, right, for U greater than U vertex. This is triangular, okay, and then we have a parabolic where W by U is U by U 1 minus y by delta square tan of beta. Okay, so we have, so these are the two basically relationships where beta, okay, is equal to limiting angle at the wall okay, and phi is limiting free stream angle. Is the limiting free stream angle. Okay, so if I were to go and look at here, so you see, so we have the triangle approximation, you know, the first one which we did. So the triangle approximation is this, where the relationship between U W by U is given by this. Okay, let's look at this plot. So this is W by W, and this is the U by U. Okay, and this Q is nothing but the basically the resultant velocity, which is U square plus W square to the power half, or under root of U square plus W square. Okay, so by okay. Now this is the, so this would be the U vertex. So you have, you know, these on, so U by U tan beta, you know, for this. Let us see. So U by U tan beta. Okay, so this angle is tan beta. Okay, this is tan of beta, right? So you can think of that. This angle is beta, okay, and this angle is phi, right? So limiting angle at the wall is beta, and limiting angle of the free stream is phi. Okay, so the first part of it, okay, is U by the same tan beta, and 1 minus U by U tan phi, right, which is for the later part. So this is how, this is the triangle approximation. This is how the triangle approximation looks like. Okay, and this is the triangle approximation, right? And now here, as you see here, this is the resultant velocity, and you can see that in the fourth thing here, you know, this is the direction of the surface shear, right? And this is the you know, resultant velocity, right, and this is the horograph, and as you can see that, you know, this is beta and this is phi, and here there is actually, you know, the triangle idea actually fails, right? It doesn't work at all. So it's not going to be able to generate something like this. Okay, so like we said that this one. So it's reasonably valid for the power law profile for modest pressure gradients. Okay, and the simplest of formulas. So we use this. There's a relationship between w and u, and when you do that, that's the photograph. Okay, and this is the parabolic. Okay, so let us just write. So now that's what we understand, and then if you come here, so now let us look at this. Okay. Okay. So the analytic approximations for the velocity. So if you see here, okay, so again this is w and this is this, and beta, which is the limiting angle at the wall, and this is the free stream limiting angle, right. Okay, so the triangular approximation is the solid line, right. The parabolic is the dotted or large, this one. Okay, and we have one more, which is quartic. Let me write down what the quartic is. Okay, it's a little more complex. So parabolic, and now we have the quartic. Okay, so the quartic is more complex, and where we write w by u is equal to tan of beta this, right, minus tan of phi into 3 okay, and this zeta is actually equal to this. So this is actually okay, this. So this is again the relationship between w and u, right. So if I go here, so that's the quartic one, the dotted, this one is the quartic. Okay. So what we see here, so obviously they don't seem to agree at all, there is some agreement. Okay. So if you see here, right, if you see here the triangular one, right, so the triangular, this is the triangular kind of, so this is the beta and this is the phi, right. So the triangular one is matching at both ends, right. So u is 0 here and u is equal to the free stream, x directional free stream, right. If you have the parabolic is matching only at u is equal to 0. Again, it's more than phi here, the angle is more than phi, right. And the quartic is interesting, right. The quartic is interesting because it's kind of matching at both ends, and here, however, it kind of deviates from the other two. Okay. All right. So that is to give you some idea as to how we can again go ahead and solve the equations, okay, and what are the complexities involved. Okay. All right. So now, that's not a very trivial exercise. That's not a very like we said, to even do the integral theories is not easy to accomplish. So we have to try different things, and that's what researchers have done, right? So now Cook, right? So it's actually not too long ago, come to think of it. Okay, so he came up with an effective solution technique. Okay, he came up with an effective solution technique with a very simple set of approximations. Okay. Okay. So the one being that small lateral velocity right, which means that. Okay. Then, okay, for let us define S, right, which is the free streamline direction. Okay, and N is the lateral direction. Okay. So, if I do that, right, then the momentum integral relations become so. Okay. So, then the momentum integral equations. What happens to them? Well, they look like this. Okay. Right. Two plus h by u plus 1 by r, this is equal to tau wall in the stream direction, this thing, right, and r is essentially the local the radius of curvature, the local radius of curvature of the surface. Okay, so I think we will just write it here, why not? Okay, this and r is local surface radius of curvature. Also h, yeah, h we have just written, I think we just wrote h. Okay, I am going to just write it again. So, h is equal to, right, this. Okay, so the momentum equations, let me finish that. So, let me the momentum equation. So, this one is in the stream direction of theta 1 1. Okay, so then the next one is plus theta okay plus 1 by r del s, okay, plus theta 1 1 by q h, right, is equal to, so we are looking at basically, so this is, so we consider two directions now, right. So, the free streamline direction and the lateral direction. So, I am writing it out in that fashion. Okay. So, small cross flow approximation, three other integrals. So, once I do this, the moment I assume that w is very small compared to u, right. So, these are the integral equations. So, this is how get transformed from what we have developed earlier, right. And the other three integral thicknesses have negligible effect. So, the only two that we are looking at is theta 1 1 and theta 2 1. Let us just go back to what we did last time. Okay. Right. So, if you look at this, so this are our we had. So, right now what we are using, is theta 1 1 and theta 2 1. So, theta 1 1 and theta 2 1, right. And so, the other three, right, integral thicknesses, right, have negligible effect. So, you have got 1 2 and here. Okay. So, these are the thicknesses that we have sort of developed earlier. Okay. So, if I do that, right, okay, let me just, so that the inference is, so the inference here is that final, or inference or comment actually, because once you do, then you begin to realize this, right. So, for the small cross flow approximations, for this small cross flow approximation, right, the other three integral thicknesses, right, have negligible effect. Okay. And let me also write here the terms involving R, so account for streamline divergence and convergence. So, terms involving R, right, account for streamline divergence and convergence. Okay. All right. So basically, this is he's trying to come up with a method where you, again you can solve these equations. So he also went Cook. I mean, all right. See, also he assumed on another occasion he has assumed. Okay, H is equal to 1.5 is equal to constant, right, in the power law profile. Okay. So, if you do that, if we do that, H is equal to 1.5, right, then this means that tau in the streamline direction, right, is this, right, and tan of beta, right, in the streamline direction is equal to this, is equal to this, right. So, if we do this, so then we get an expression for the wall shear stress in terms in the streamwise direction. Okay. And so this is actually, so when we if you kind of do that, so this is essentially a zero order method, okay, which is extremely simple but not accurate, obviously. Okay. So, it is extremely simple, but not accurate. Okay. So, now having spoken about this, all right. So, so essentially we wrote out equations, we came up with an integral theory, right, and then we saw it's not very trivial to get solutions for these integral relationships. So we tried different things, and we've looked at the pros and cons of that. Okay, and I think that we discussed, we saw so we looked at three possible relations, right, between the lateral and the W and U. Okay, the formulation with that, and this is how it looks like. Okay, this is all analytical approximation of the velocity hodograph. Okay. All right. So, I think now although let us now, since we are talking about turbulent boundary layers, so let us look at the law of the wall, right. So, now I think we have mentioned earlier that even just formulating the law of the wall is very difficult. Okay. So, let us see what that means and what exactly we can do or not do with it. Okay. So, let us look into that. Okay. So, 3D law of the wall. So, let us here what we will do is let us assume, okay. So, let us assume the resultants surface shear stress. Yeah. So, the resultant surface shear stress, right, is tau okay. This, right. So, let us assume that the resultant, so the tau wall, right, in the x direction and z direction basically. So, and I am taking the resultant of that and I am going to call that as this. Okay. So, this has been measured. So, this is measured. So, let us assume that this has been measured. Okay. I am able to measure this. Okay. Has been measured. In a 3D boundary layer. Okay. Now, then in that case, right, where we look for a quantity V, right. So, now in that case, now we look for a quantity V, right, which is actually effective velocity okay, that correlates the velocity profile right into its 2D form. Okay. So, essentially, and this one, so we can just look at this. So, this V is V by okay, is okay. Okay. So, now we are trying to look for a quantity, an effective velocity, right, that correlates the velocity profile into its 2D form. Okay. So, so we are trying to do something like that, and we are looking at velocity v, right. So, now this has been this has been researched by several researchers on for such a long time. So, I am not writing giving you details of that. You should be able to figure that out from some of this material has been taken from F.M. White viscous flow. So, you can look at it there and you can look at all the references, etc. It would actually be nice to do a literature survey, and also some of the things that I am talking about is from his book. So, it is very it basically has data from research which was done near about that area. So, 1970s. I don't think I've seen anything from 1980s. So, it's about in the 1970s, right. So, I think that one should be able to do literature survey at for more recent times and see what kind of work has been done. But I think this is good to sort of lay the benchmark, or lay the grounds, rather not benchmark, lay the grounds to kind of figure out that what work actually has. I don't think I was trying to do a literature survey here. What I was really trying to understand is what is the difference in the formulation between in the formulation between a 3D and a 2D. What exactly is the complication here? But it so happens that the complications are just manifold, and you know, it just, some of the things just don't you know, which we did earlier actually have actually no meaning, right. So, we are having to sort of relook at several things, and since we said that the 3D law of the wall is just very difficult to you know, formulate, and the 3D wake is almost impossible. Okay. So, we have talked about this. Now, regarding this V that we just you know, this effective velocity, right. So, this several people have given suggestions, right. So, I am going to write that down. Okay. Several suggestions. So, let us just say the suggestions and by researchers, right. So, suggestions researchers. Okay. So, this one here V can be, it can be U, right, it can be Q, which is nothing but, this is what I just said, okay. This, then it could be Q cos of gamma, okay, U sec beta, okay, and arc length is equal to 0 to U 1 plus dw du, okay, du. Okay. So, these are some of these, the one. So, this is actually 1, 2, 3, 4 and 5. So, we basically have 5 suggestions for this V from various researchers, okay, and I am going to represent that physically. So, let us just say that this is the W and this axis is this, okay, U. Then let me first draw the photograph of that. Right. So, this is the photograph, right. Now, then, okay, let us just say, so this is the direction of you know, U, okay. So, let us just say then Q is something like this, okay. So, this is Q, okay. Now, then this one is beta, okay, and this is the gamma, okay. All right. So, if this is the Q, right, then what I am going to do is drop a perpendicular, right. Let us just increase that, right, and then go along the tangent and do that, okay. So, then I am going to call this as A, right, B and C, right. In that case, right, so AC, this is the so this will be my U, this will be my W, right, and B, this one is Q, right. So, then so now essentially what we are trying to do is, if you see here the possibility of V could be U, could be U or Q, okay, Q cos gamma, U sec beta and the arc length, okay. So, I am trying to represent that you know, graphically here, right. So, then if you take, okay, so I am going to do this, basically, okay. So, I was trying to do a tangent right there. Okay, let's try that again. So, yeah, that should be. Is that better? Yeah, probably this is better, right? That. Now, this length, right, this length is, right. So, this length is actually q cos nu, right. This is my q and this is going to be q cos nu, right. And then we also have u sec beta, yeah. So, that one we also have yeah, u sec beta, right. So, now here you see cos beta, right, cos beta is u, right, u by AB, right. So, we are looking at in the triangle. So, the triangle A, B and C, right. So, cos beta, right, is equal to u by AB, right, or AB is equal to u by cos beta, or AB is equal to u sec beta, right. So, this length AB is actually equal to u sec beta, okay. And the arc length represents is of the hodograph, right. So, the arc length is of the hodograph. That okay. So, this is the arc length is that of the hodograph. So, we have basically looked at what this velocity v, effective velocity that we are trying to look at, and how I am trying to represent that on a graph, So, that is for me to understand, right. So, you have u, so you have u, then you q cos, you have u, you have q cos gamma, then this is u sec beta, and this is the arc length of the hodograph. Okay. All right. So, I think that that's it. I mean, I don't think I am going to talk more on this, right. So, this is about this is all about it. Okay. So, we have looked at, so we said earlier that the 3D wall is very difficult to accomplish, in 3D and etc. But this is where so we came up with something. So, we still looked at, what is the difficulty, and is there a way about it or way around it, is there something that I can do. But anyway, so this is something that these are the lines on which research has been done, so far. Okay. So, so basically that, and you have and then we looked at the 3D law of the wall. Okay. And essentially we basically started from here saying that our integral theories. So, integral theories, why do we need that? So, what is needed in the integral theory is essentially empirical correlations which can close the integral relations, right. So, we basically looking for closed form solutions, but well, hitting at roadblocks every step of the way, I guess. So, here we use the power law profile, right, which is again it's something like this kind of it's basically we are trying to approximate or sort of gauge or guess, so to speak, is the velocity profile u by the x direction velocity profile. We basically try to put it in simple words, right, this power law profile. What exactly are we trying to do? Well, we are basically trying to guess the velocity profile in the x direction. That is what we are trying to do, and we write that as here, right. So, this is not, this is okay as far as modest pressure gradients is concerned, right, but this does not, is not able to, it does not work very well near the separation points, right. And then we took kind of simplest of formulae. So, this is the triangular rule, right. So, we looked at that, triangular and parabolic. So, you can see that here, right. So, we have kind of a parabolic, this is going to result in a parabolic polynomial, okay. And this one is like triangular, okay. Okay, so if I do that, and then it was the quartic. So then we also took something which is a little more difficult, right, quartic, and then this is how it looks like. And if I do that, what we saw was this. Okay, so then we looked at this plot, right. So the triangle approximation. So W by this thing. So W by U, right. So this is something where it seems to work, right. But here the triangle idea actually fails. Okay. Somewhere here. Okay. So, now I am going to stop here, right. What we will, so as of now, so we have looked at the Bernoulli equations, and we are basically trying to look at ways and means where I can solve these equations. I have set it up, and I have tried to do different things with it. I am still kind of struggling with the fact that it is way too complicated for me to calculate it, and that is what we are trying to do. Okay. All right. So, okay, so we will do something in the next class, which will be different. So, I thought it would be interesting, okay, to look at, because we constantly talk about CFD, and we think that just pressing a button is going to give us answers. I would appreciate that if you can really look at the equations and look how they are set up, and see how the formulation is conducted, the algorithm is developed, to actually get those big softwares to work, right, which you kind of press of a button and just enter a couple of things, and that is it, right. However, I think it is really more interesting to kind of know what is actually going on inside. Okay. So I thought it would be relevant. Okay. I thought at least to give you some idea as to, if I were to set this up as a finite difference problem, how would I go about it. So, we looked at integral theories and all of these things, right, the analytical approximations, etc. So, I would also like to do the finite difference method, and look at it a little bit more in detail. Okay. So, we will do that, and for now I will stop. So, thank you.